Okay, so we have in the startup. Okay, so we have with student numerical analysis, and we have with Euler. Okay, so we have d over dx. Again, so we have for your y, okay, have y with respect to x. Okay, and we have is equal to, and again that was x times y of x, and we have plus 3. Okay, again we had that y naught, okay, was equal to 1. And let me double check here. So you have, yes, that y naught is equal to 3, y1 we're looking for. Okay, so y naught is equal to 3, and we're looking at going out to x is equal to 1. Okay, now we had the step size, okay, to be at 1/2. So we have like number of steps. Okay, you're going with 2, and okay, and we have say we have for the digits. Let's say we have expanding out to, we'll say 10 digits, and if I want to put the information in table format, okay, just how the outputs progress from one stage to the next. Okay, so we have with the Euler, okay, so we have this equation, x times y of x plus 3, y naught is equal to 3, and have x is equal to 1, and we're going to find out, okay, just what the y value will be at x is equal to 1. So we've got 2 steps, 10 digits, and for output is equal to information. I'm just kind of narrowing it down here. So if you notice, okay, we have with the Euler output. Okay, so when x is 1/2, the Euler method value was a 4.5. Then once we get x is equal to 1, we have 7.125. Now, for what we have in the column over to the left, this is the exact solution for what we have in Maple, and this is the size of the error, okay, which is pretty substantial. Now, and if I were to take what I have looking at the improved Euler method. Now again, they call it the improved Euler, but the opening statement is not Euler, it's Runge-Kutta. And it had the same opening line, same number of steps, and have digits equal to 10. Now you're going to have for the sub method, okay, that's HEUN, the Hoyne sub method. Output is equal to information, return, okay. And so we have with Runge-Kutta Hoyne, and that is that 9.1523 number. Let's see if that is, we have a one-to-one correspondence. Yep, 9.15234375. And as for what we have in the case of the Runge-Kutta, the official Runge-Kutta, now the sub method, okay, this is going to be RK4. Okay, so the sub method is going to be RK4, and for the output. Okay, so the Runge-Kutta, okay, in 2 steps. So we had this number 9.176478, and that's very close to Maple's numeric solution, 9.178222. And if you notice, we have for the sizes of the error. Now Euler, you have like 2.053, way off. Improved Euler, your size of error is much smaller at just under 0.03. And in case of the Runge-Kutta, okay, have right at 0.001. Okay, now let's say that if we have a case and we're looking at, let's say, just solving an equation through, say, the numerical methods. And I'll just say that if we have So we have dy over dx, okay, and we'll say is equal to let's say you have 2 times x to the 5th over y squared. And we'll say that we have for the input conditions, okay, we'll say that we have y of 2 is equal to 3. So we have y of 2 is equal to 3. And we'll say we want to determine, okay, just what y of 4 is going to be equal to. And let's say that if you have, let's say we have let h be equal to 0.1, and we'll try it out also with h at 0.05. Okay, so just looking at what we have with, say, just starting out with Euler. Okay, now just looking at what we have, okay, so you got your step sizes, you have a 0.1 and 0.05. Now for the number of steps, you're looking at transitioning from x is equal to 2 to x is equal to 4. Okay, so we have at h is equal to 0.1. Okay, so if you were to enter like the number of steps, okay, so you're looking at the final value of x minus the initial. So you got 4 minus 2 over 0.1. So you have 2 over 1/10. So you're going to have 20 steps in the process. Okay, and now, okay, this is where the step size is 0.1. Okay, and so we have an entering. Okay. Okay, so you got Euler. Again, we have dy over dx. Okay, so you have d over dx, so y of x. And you have 2 times x to the 5th. Okay. And you have all over y, not just y, but y of x to the 2nd. Again, we have that y of 2 is equal to 3, and we're going out to x is equal to 4. And again, we have with the number of steps, okay, with the step size of 0.1, so you have number of steps is 20. And we'll say that we have for the number of digits, we'll just keep this to 5. And just kind of have a tabular display. So you have output is equal to information. Let me see. Oh, I'm not looking for a vector product. Comma. There we go. All right. So we have for the display. Okay. All right. So we got Euler. Okay, we have 2x to the 5th over y of x squared, and you have y of 2 is equal to 3, and you have going out to x is equal to 4. So your step size again is at 0.1. Number of steps is 20, and again we have just looking at the progression, and we're going out to x is equal to 4. Okay, notice we have going only out to 2.8, but what I want to do here is that I can just click on show all. Okay, so getting it down to 4. Okay, there we go. So we have with the second column, we have Maple's numeric solution, and you have the Euler counterpart. Now for this equation, the Euler approach, not too bad in terms of the amount of error. Much smaller in comparison to what was used in the first equation. So Maple's answer, the correct answer, we have 15.952, and we have with the Euler, you have 15.891, and the size of the error we have 0.06. Okay, so you have with Euler, say about 15.891. Okay, and that's for the step size. 0.1. Now, if I were to reduce the step size, okay, so my number of steps would double. Okay, so in this case I would have like 2 over 0.05, and this would be at 40. Okay, so if I were to duplicate what I have in this command, the number of steps, okay, so same line of information. Now the number of steps is going to be at 40, and okay, and if I just go to show all, okay, and this time we have okay, so with Maple's answer you have 15.952 again, and we have with Euler with the step size at 0.05 you have a 15.922, so you have a little bit smaller an error size. Okay, and so we have in this one case you have 15.922. Okay. Now, in terms of the improved Euler, I'm just going to say IE. IE for improved Euler, not industrial engineering. Okay, so, all right. So we have so for the improved Euler, okay. Again, for your opening statement for the improved Euler, okay, the opening word is not Euler, but Runge-Kutta. You got the same equation, and for the step size at 0.10, okay, so number of steps is 20, digits is 5, and now the sub method, okay, again, H-E-U-N, Hoin. And then we have returning, and again, since we're going out to x equal to 4, so if I show all, and in this one with the improved Euler, okay, so that is going to be 15.956. And again, if I doubled the number of steps, okay, so going from 20 steps to 40 steps. And once again, showing all, with the show all command. Okay, so we have in this one, okay, so you have very close. So we got 15.953. And we have with the Runge-Kutta, it is going to be virtually an identity, okay, when you round to the nearest 3 decimal places. So you have with the Runge-Kutta, okay. So for the step size at 0.10, and the sub method is going to be RK4. Okay. Again, so you have the display up to 2.8. Again, for the Maple 2020, okay, so we go to show all. And again, you're going to have to the nearest 3 decimal places an identity. But if I were to carry out to more decimal places, I would have this error size, like 0.0003. It's 15.952. And we're doubling the number of steps. And we have the same number to the nearest 3 digits. So that was number of steps at 40. Yep. Yeah, so you still have 15.952. Okay, and we'll be looking into some other cases with the numerical methods, and now just kind of going back to some of the earlier techniques. I'm going to be sending out some Maple labs, some of them going back to earlier topics, and okay, say we have in the case of Maclaurin series, and with what we have in Maple, and I'll do here, just go to a new worksheet. Okay, and say if we have, like in the case of an opening line, so if I have for Maclaurin series, okay, so if I have like series, and we'll say like we have e to the x, and I want to have for the statement, and say if I'm looking at the first terms in the mix, okay, so I want to have, let's say for instance, okay, so I want to have x, say like just for the first so many items, so I have x going from, let's say 0 to 10. And I'm looking at the, say the Maclaurin series expansion here. Okay. And you don't have to throw in an opening line. Okay, so if we're looking at Maclaurin series, I think you need to start out series, and for e to the x, you need to take the e symbol from the left. Don't just type in the letter e, or if you type in anything, it's with exp of x, and you have x going from 0 to 10, return, and voila. Okay, so you have all these items that are in the mix. Okay, so you have like the first 10 terms. You got 1, 2, 3, 4, 5, 6, 7, 8. Yeah, and you got that O x to the 10. Okay, and what this means, and I looked it up in Maple, and what this means is that I looked this up. Okay, so if you have a series and you have for this statement, if the series like there's some room for like a certain minuscule percentage error, like if the series is not exact then an order term, this is what that O is. Like for example, O of x to the 6 would be like the hypothetical last term in the mix. Yeah, and so you have order x to the 6, and the reason that is thrown in is that technically for the exact terms, okay, the series is going to be running continuously. So for Maclaurin series, the only command you need is just series, and if I just something like series, and we'll say we have like the sign of 3x, and we have like in terms of the degree, let's say we have x going from 0 to, let's say x from 0 to 12. Then we have with the return, and again you had that O x of 13 means that there's that certain room for error, because we're looking at just the first handful of terms among infinitely many that will make up the Maclaurin series for the sign of 3x. Okay, so your first term, you have a 3x, next you have 9 halves of x cubed, 81/40 of x to the 5th. Yes?
For those, do you load any packages into Maple, or is it just straight inputting?
Just straight input. Yeah. At least for Maple 2020, and I think even for like going, so I know within the last few years, hey, going back to I think it's like Maple 2017, I think series would work. So yeah, series would be your opening statement, and just like series, And say we have like 1 over 1 minus x. So you have x going from, let's say, 0 to 12. Once again, so you had that progression. So you have 1 plus x squared plus x cubed, x to the 4th, x to the 5th, and so on. And say if I have something like series 1 over, watch out, let me do this. I'll say I have like 1 over the tangent of x. And say I have x going from 0 to 10. So you have among the first items, you have like x plus 1/3 of x cubed, 2/15 of x to the 5th, and so on. And if I had something like the cotangent of x, okay, this is what you would have in the process. So it's series cotangent of x. And say if I double the angle, okay, say I have like 1/2 of x to the -1 minus 2/3 of x minus 8/45 of x cubed. We have minus 64 over 9/45 x to the 5th. So these are just your regular series, like in the Maclaurin.
How many tangents and cotangents can you do before it breaks maple?
That I do not know. That's a good question. If I tried out like 100, woo, yeah.
That was almost instant too.
Yeah, yeah. Maple can do a lot of things, but again, there are some problems out there that can be so transcendental, especially with crossing over to improper integrals and all that, or especially like anything that kind of, I guess like in physics, kind of almost reaches like a singularity or whatever, and so it can just kind of create an unstable situation for maple. Now, so just for regular series, the Maclaurin series, Taylor series, you just have series. Now, if you have, let's say, when we looked into series solutions, and we say that if we have okay, so we got tools, tutors, differential equations, ODE analyzer. So again, okay, and we'll say 3 times y of x. No, 38, 3 times. So I add this. Click on done. And then we have solving symbolically. Okay, now I'm going to put this in terms of a formal series. And solving case, I'm going to have this particular expression. What you can do, okay, is that for what we have in this display, okay, and let's see, expand. Maybe it's going to be combine power. Combine the powers. Combine, not simplify, but combine. So if you notice, got 3 to the n times x to the n, so you have 3x raised to the n. Now, for the gamma of n plus 1. If I copy this statement, type in convert, and then I have just type in factorial. And then entering, okay, so I had the factorial notation. So before I had the original answer in terms of the gamma function, but if I type in the command convert and just take this and then just enter a comma, factorial, this is going to be your answer. And this will be like a constant and this is like your compressed series notation for what represents e to the 3x. Okay, and let's say that if you have, okay, say we have, for instance, okay, if we have let's say we have a homogeneous equation. We have like y double prime plus 4y is equal to 0. And now we're going to put this in formal series terms. And again, we can go back to the ODE analyzer. Okay, so we have in terms of the tools, tutors, differential equations, ODE analyzer. Okay, so you got this particular portion here. So you're gonna have, again, so tools, tutors, but again, it's for the older models to see the other pathway. 2020 is tutors, but the other one was assistance. But tutors, you got differential equations, ODE analyzer. So I got this table on display. Now in terms of editing, so go to assist. Okay, so I'm looking at y with respect to x of second order inserts. So I'm good with this one. Okay, and then I'm going to have plus 4 times y of x is equal to 0. Okay, and after, if I'm satisfied with this being the entire equation, so I'm going to click on add. So it must be quadratic. Okay, 4 times y. Okay, I wanted to here enter too many parentheses. Okay, so adding. Okay, just click on done, and then we have solving symbolically. Okay, instead of the default method, again I'm going to go with the formal series, and then clicking on solve. Again, I'm going to have this particular display. Okay, and I'm just going to quit just to get the, just get those notations set up. Okay, so we have, and now looking at what we have, just sort of making the adjustments. Like if I want to put this in factorial notation, yes sir. First of all, if there are any powers to combine, okay, and okay, so we got this particular layout. Okay, so you don't have anything to combine, or let's see. Yeah. So there were no like powers to combine. Okay, but I can convert what I have in terms of factorial notation. So if I take this display, I'm going to get, so converting what I have here and for factorial. Okay, and this is going to be our display. Okay, so again, before we had the solution in terms of the gamma notation, and again, like your gamma of m, 2n plus 2, that's going to be the factorial 2n plus 1. Okay. So so this will be the output, okay, that we have in making the adjustments for combining any like powers, okay, and we didn't have any to exist, at least not in this, like in the sense of what we had with the previous example, but we do have the capacity to convert from gamma notation to what we have in factorial terms. Okay, now there is another part here. So this is what you have with the really complex series notations, all that, where we had the gamma function, and also working with factorials. And also, another case, with the Laplace transforms. Okay. Now there is going to be an opening statement on this one. Okay, and this is going to be for Laplace transforms. And that is going to be, if my memory serves me, so you can have with int trans. So you have IN, okay, not INTRANS, but INTTRANS. And now if I'm looking at the Laplace of, say, a t term, so you have like Laplace, and we'll say we have like Laplace of 1 going from terms in t, like your t is your input variable, s is going to be your output variable. So you have Laplace 1ts, and the result here is going to be 1 over s. And say if I have like Laplace of cosine of 3t plus, let's say let's see, e to the 5t, oops, okay, so I have expression in t, and the Laplace variable I'm going to have in terms of the letter s. So this is going to be what you have here. So just combining, okay, so you have 2s squared minus 5s plus 9, and you have all over s squared plus 9 times the quantity of s minus 5. Okay. And let's say that if I have and so we have something like the Laplace, and I'll say I have the square root of t plus the sine of 4t okay. Now I got these terms here. Now, okay, so this is the Laplace of the square root of t. And this I have with 4 over s squared plus 16. Okay, and now if you're looking at like taking these terms here, and let's see, we have like simplifying. Let's see what this does. Yeah, so if I simplify and go with symbolic, if I want to make this into one overall expression, so you have simplified, symbolic, combining the fractions, you get this overall ratio. Okay. Now let's say that if I'm going the other way around, because we took like terms in t and converted to the Laplace transform counterpart. But let's say if I wanted to go the other way around. Okay. For your command, okay, this is going to be INV Laplace. INV for inverse Laplace. And we'll say that we have 4, yeah, we just solve 4 over s squared plus 16. So you got 4 over s squared plus 16. Okay, so the Laplace you have in terms of s, inverse Laplace, we'll put in terms of t. And the result here, that is going to be the sine of 4t. So you got INV Laplace. So you got 4 over s squared plus 16, and you have with s and t. So the output we have at again as the sine of 4t. And if I have something like inverse Laplace, and we'll say that we have I'm going to see what it says if I put in like 1 over the square root of s. I might get a weird readout. Say I have 1 over the square root of s, and got s and t. All right, so I got 1 over the square root pi times t. Okay. And we'll say that we have something in the mix. I'm going to see what happens here if I have so I have something like s squared plus 3s plus 7. say I have like all over s plus 2 raised to the third. Okay, all right. So it gives the factored form here. So you have e to the negative 2t quantity, and we have times, okay, you have 5t squared minus 2t plus 2 all over 2. Okay, so again, with Laplace and inverse Laplace transform operations with Maple, you do need that opening line with in parentheses int trans, and then you have followed by the colon. You have something like dy over dx is equal to x squared plus y squared. And I can say something like y naught is equal to, let's say y naught is equal to 1. And I want to find out what y of 0.5 is equal to. Okay. Now, we'll show you just a couple of versions here. Okay, so you have dy over dx. Okay, so you have equal to the sum of the squares of x and y. And I have y naught is equal to 1. And I want to find out what y is going to be whenever x is at 1/2. Okay. Okay. So if I go into, say once again, the ODE analyzer. So we have y with respect to x, and again this is a first order differential equation, or at least a first order in the derivative. We're going to have equal to x to the second, and I have plus not just y but y of x to the second. Okay. This is what I got here. Okay. Then we have solving symbolically. Okay. And if I go with the default method and I solve, this is going to be not the most attractive display. And once I quit, okay. So, but for what we have here now. Your solution with the initial condition, okay, you have like your Bessel function, and that which has the letter J, that is a Bessel function of the first kind, which we kind of look into, and that Y we're not going to mess with, that's the Bessel function of the second kind. And now, so this is what we have with the initial condition. Now, taking what we have here, and say if I approximate, let's see, or I should say I'm looking at whenever x is at 1/2. So you can go with evaluate at a point. So if I evaluate at a point, so if I have x at 0.5, okay, I got this this particular display, and just taking what we have now. Okay, so if I want to convert this into approximating, okay, so if I approximate to about 10 decimal places, so this is going to be about a 2.066999714, and see how the numerical methods might show up. And let me kind of do this. If I were to go out to x is equal to 2. Okay, 0.31125. Okay, and in terms of the capability of the numerical methods, okay, so if I go and try out this equation, okay, so again for numerical methods, okay, and for you become eager to type in Euler, we're going to go cut it and all that. Okay, remember, got to enter your opening command. So you have with student numerical analysis. Got with Euler. Okay, so the differential equation. Let's see. All right, so you have d over dx of y of x. Have equal to x squared plus y squared. Again, we have y naught is equal to 1. And we're looking at, again, the destination value of x to be at 1/2. And we'll say that for the step size, we'll just let this be at 0.1. And num steps at 5. Okay. Yep, so you have going from x equals 0 to x at 0.5. So we have with the Euler. Okay, so your maple numeric solution, you have right at 2.067. This is the Euler results, and this is the error sign, say 0.2299. Okay, now again, we have with the improved Euler. Okay. Again, so with the improved Euler, okay, so you have the sub-method. Okay, so you have that Hoyne sub-method, and okay. And what happens here, let's see, is that, what I did here, sub-method. Not sub-method. Okay. All right. So you have in this one. Yeah. So there's no v in sub-method. Okay. So you have for the output. Okay. So you have Maple's numeric solution. Okay. There we go. Okay. So for the improved Euler. Okay, so you have Maple's numeric solution at 2.067. Riccati at 2.049, so we're in closer proximity. And we have with the Runge cut, okay, so the sub-method instead of the HEUN, the official Runge cut, okay, that's going to be RK4. Yeah, and so for the Runge cutter, now that one very much in close proximity. In fact, for the Runge cutter, now with the improved Euler, have 0.01823. Not a bad error size, but with the Runge cutter, percentage-wise, it is much closer in proximity. Where you have not 0.018, but 0.00003898, and that's just for 5 steps. Now there could be some situations where some of the inputs can be unstable. Okay, and say if I have, if I were to go back, and we'll say, I'll keep the step size the same. Okay, so for number of steps. So if I'm going out to x is equal to 2, and I keep the step size at 0.1, okay, there might be an unstable situation here, and in fact, okay, now this one does stabilize. Okay, so you have showing all. Yep, this is what's going to happen within certain parameters. And I've seen this with some of the differential equations that might have, like for example, you might have some differential equations whose solutions might stem with taking partial fraction decompositions of the independent variable. Now between 0 and 0.5 we had good numbers, but what happens is that I think there's something in the mix with the Bessel that if you try to take writing this out in algebraic terms, like stuff like the Bessel function, and try to put it in numerical terms, I think there's like a division of the input somewhere where you have trying to apply numbers with the numerical method. It sort of reaches a singularity, and we have with the Euler approach again. So you still have, from 0 to 0.5, that is good, but once we get beyond 1, it kind of gets to a point. It looks as if you're dividing by something that is like 0 to the right. So you had like that float undefined, and so essentially the whole thing blows up. And it's not going to get any better. Okay, so you have Runge-Kutta submethod, the Hoyne, and it's going to come out to pretty much the same kind of situation. It's because within the parameters expanding on out to x is equal to 2. Okay, so it looks okay so far, but if you notice, you have for the error size, let's say within, the first items, okay, error size not too bad, but if you notice, it starts to kind of build up, and once you get out to x is equal to 2, it's like the error size, it just becomes unstable. So you have like 0.04, 0.12, 0.4775, 3.952. So it's kind of like the larger the input gets, it's like the growth of the output with the numerical methods becomes exponential and unstable. Okay, and and submethod, you have RK4. Again, so far it looks okay. The error size doesn't look large, say whenever x is less than 1. But as I look at showing all, again, you had, once you get to x equal to 1, it's like the whole thing just blows up once again. Okay, so yeah, so numerical methods, they can work in a lot of situations within certain parameters, okay, especially ones that don't run the risk of heading out into a singularity. And if you were to try to, well, I guess it's kind of like there's a fine line where you have essentially the difference between genius and insanity, and that is success. So weren't too successful with that one. Okay, so numerical methods, they are reliable, especially if you're looking at integrals like along the lines of single variable calculus and all that. But once you get into like where because at least you have the output equations where the output is dependent upon what's going on with the input, but you have like those equations where the output is contingent upon what's going on with the input, and also how the output is responding as the input is changing. And and as the input starts to change, it's like the output is kind of like it overreacts or whatever. And so that's kind of what's happening with the numerical methods.